Hi, I'm Evan Rich. I'm a postdoctoral researcher at the University of Michigan. And today in my talk, I want to talk about are small dust grains actually coupled to the gas in protoplanetary disks? Now, this is an assumption that we commonly make, especially when modeling protoplanetary disks. And when I say small dust grains, I really mean around 1 micron or less. And the gas I'm really talking about is the CO gas, in particular the 12 CO gas we're going to be measuring. In particular, the influence of the gas, and especially if there's sufficient turbulence and if it hasn't settled, the gas will have some flare shape to it, the scale height of the gas, as a function of midplane radius. And the small dust grain should have a very similar shape that might be at a slightly different scale height, but relatively similar in shape. Now, while this is commonly assumed, it hasn't been measured up until now. However, with the advent of new observatories like ALMA and high contrast scattered light imaging surveys, especially instruments with like the Gemini Planet Imager, we can actually measure that now. And so first I want to talk about how we're going to be measuring that. And we're really taking advantage in both of the case of the small dust grains and with the 12CO gas, we're taking advantage of a geometric effect of when you take a 3D object and project it onto our 2D sky. So let's start with the small dust grains. It has to be a ring. So it's only protoplanetary disks with rings or multiple rings in this case. So when you start on the edge-on case, so you're looking through the protoplanetary disk, you have your star, your midplane, and the light is going to be scattering off some scattered light surface layer, and that's what we're going to be observing. In the edge-on case, you'll have a top layer and a bottom layer. We won't really ever observe this bottom layer, so the top layer is what we're going to concentrate on. When you go to the face-on, it's going to be a perfect circular ring. But when you go to the incline case and you look at this top disk surface layer that we're going to be observing, it's going to be offset from where the star is due to that geometric effect of a 3D protoplanetary disk projected onto our 2D sky. This has been observed a couple times in the case shown here of HD 163296 from Meunier et al. 2017. You can see the ring structure seen in the data. The star is over here, and you can see that the ring is visibly offset from the center of the star. And for reference, they plotted the black solid line as where the midplane is projected to be there. This similar effect can be used for the 12CO gas. In this case, we don't have discrete rings, but in fact are measuring the 12CO photosphere. When the 12CO photosphere is projected onto the sky, it's going to create these horseshoe shapes, one for the upper layer and one for the lower surface layer. I plotted on here where the midplane would be located along the major axis. And you can see that this is strongly deviated. So if you measure the deviation of this horseshoe shape from where it's projected to be on the sky, you can measure the height as a function of radius. So to create our sample, we're only using archival data in this case, one in the case from the ALMA archive or ALMA surveys, and the other for various previous scattered light surveys. It needs to have multiple rings. It needs to have plenty of CO gas that's easily detected with ALMA at an adequate resolution, both spatial and spectral. It also needs to be at a moderate inclination. This geometric effect only works at a moderate inclination. And when you throw all those things in, what's available on various previously published data and archives is IM loop, HD 163296, and CU-CHA. These objects really don't have very much in common, except for the fact that they're protoplanetary disks. One's a T-Tauri, the other two are Herbigs. They all have a moderate inclination. IM loop is the youngest, while HD 163296 is the oldest, of around 7 megayears. IM loop and CU-CHA have 4 rings, though, however, we're only going to use the 2 inner rings for CU-CHA, as the outer 2 were detected via total direct imaging, not scattered light, and the data reduction can influence the shape of those rings, thus influencing the true measured height. For the 12CO gas, the data from IMLOOP and AHD 163296 is courtesy of the D-Sharp survey on their online archive, and then CU CHA is directly from the ALMA archive. So what do we actually measure? Let's work through these for all three cases. The IMLOOP is first. For all three of them, we're going to measure the height as a function, as in units of AU. And on the x-axis, we're going to have the mid-plane radius also in units of AU. The black line is the 12CO emission layer of the 12CO photosphere. The green dots are the measured height of the scattered light rings. And then the dashed lines are the measured power laws for these things, assuming some flare angle located here in the upper left. For the first ring, the emission layer of the 12CO is at the same height as the scattering surface of the 12CO gas. So they're probing a similar layer in the protoplanetary disk. However, if you go out radially, you can see that the two flare shapes are very different. The small dust grains are at a much shallower height as a function of radius than it is for the 12CO gas. So this is a little contrary than what we anticipated. We see a similar trend for HD 163296, again showing the 12CO gas in black and the two rings in green. The emission layer of the 12CO gas and the scattering surface of the small dust grains is similar at small radius, but different at larger radii. However, our last object, CU CHA, appears to break this mold, where for the two rings that we observed, they show a very similar flare power law compared to the 12CO gas and the small dust grains here, where they appear to be emitting or scattering from a similar layer in the protoplanetary disk. So in the case of IMLOOP and HD 163296, we appear to see a trend that we didn't necessarily anticipate seeing, where we see this divergence as you go to larger radii. However, in the case of CU CHA, it really confirms what we expected to see. Even though these are only three objects, there doesn't really appear to be a clear trend via age and mass. IMLOOP and HD 163296 are the most similar. However, they're the most dissimilar. IMLOOP is very young and a T-Tauri, while HD 163296 is the opposite. So we're really going to need a lot more of these objects to really fill out the demographics before we really see any trends. But for right now, we really don't see any of those in terms of simple stellar characteristics. So one thing I've been very careful about in this talk so far is distinguishing between the emission of the 12CO layer and the actual scale height or the Gaussian distribution of the gas and the respective dust itself. And that's something to be careful about because these are observed quantities, not necessarily the intrinsic scale heights that we are actually observing or we want for modeling. And so what we did is we took a radiative transfer model torus and we assumed some normal Herbig protoplanetary disk parameters. And we took those scale heights and produced the observed scale height. So the observed scale height of scattered light for the small dust grains and the observed photosphere for the 12CO gas, producing data cubes that we had previously and put them through the same algorithms that we used for the 12CO gas and the small dust grains. And in fact, we appear to see almost identical flare angles or power laws for the small dust grains and the 12CO gas. So the things that we're observing with IMLOOP and HD 163296 diverging as a function of radius doesn't really appear to be a function of observation. It's not an observational bias that we're seeing, but it's actually truly probing the intrinsic scale heights of the dust and gas respectively. So what could be causing this? One aspect that I don't have showed here, but it could just be simple settling as a function of age. However, one ends up being older, one's younger, so it's not necessarily clear, but more investigation is really necessary to investigate that aspect. Another is a simple observation of the gas to dust ratio. So this is taking analytical models, the William and Best 2014 analytical models for the CO gas, the photosphere of the 12CO gas is the dashed line here. Similar plot to what before, the height in AU versus midplane radius in AU as well. And then the small dust grains, assuming 1 micron for pole 2017. These are the colored solid line contours here. And you can see that as we increase the gas to dust ratio, we decrease the observed scattered light small dust grain height. The global gas to dust ratio might be an explanation for the features we see and why objects like IM loop is very different from objects like CU CHA. So in conclusion, our original question, are small dust grains actually coupled to gas and protoplanetary disks? It's not necessarily clear. It's definitely not true for all protoplanetary disks. Objects like CU CHA, that's a very valid assumption to make. But for objects like IM loop and HD 163296, we do see a divergence as a function of radius. So more observations are necessary. More rigorous modeling is absolutely necessary. Thank you very much for listening to this talk. Feel free to ask me any questions in your so choosing method due to the remote nature of this. And you also feel free to contact me via Twitter or email me as shown on here. Thank you again for listening to my talk, and I hope to chat with you all in the future.